Hello, good afternoon. Can you hear me well? We're starting now. Can you hear me? Yes, you can. Okay, fine. So, first of all, I would like to hear from you about your project process. Can anyone tell me, please, what you have been doing last time? What kind of laboratory assignment you are on at the moment? How is it progressing? Any problems? Any questions you would like to discuss? Anything you would like to share with me about our laboratory work? Nothing at all? No one would come forward? Okay, Yelena says, we analyze synthetic data, removed noise using the multi-MLE maximum likelihood estimation method. Great. Okay. Okay. I see. Okay. Can you remind me, please, what kind of maximum likelihood estimation did you use? To use the maximum likelihood estimation, you need some kind of model which provides you with the probability density function. So what kind of probability density function did you use in this case? Okay, so you model the signal with the multivariate t-student distribution, check the correlation of components, great. Fine. So that's what I would probably like to discuss in a little bit more detail today. In the sense that we would like to make a distinction between two effects. We briefly touched upon them already. The effects of correlation and cointegration. And we'll not start with any a priori assumption about our distribution. It is, of course, very advantageous if we know that our signal can be modeled with a, let's say, multivariate t-student or any other type of distribution. But in general, we might not know. So let us step back a little bit and consider a little bit more general idea. We'll start with stochastic processes. And then from those stochastic processes, we'll try to understand what kind of joint distribution we might have and what should we do with that distribution. Okay, I start sharing my screen. And, because I'm sharing my screen, I might not be able to see the chat. So if you would like to say something, it's really better to say using your voice, because otherwise I can miss your chat messages writing on my virtual whiteboard. Okay, so let's go. Okay, so in general, let us probably do the following. Let us consider two, initially only two, stochastic process. What we are doing can very easily be generalized to a number of processes more than two. It is very important that the picture we are going to paint here is significantly different between one process and two. One is relatively trivial. We have already been studying the stochastic dynamics of one-dimensional process. That was relatively simplistic. What is not so simplistic is that when we really start moving into dimensionality 2, 3, and so on, but it is this quantum leap from 1 to 2, which is important. So we would say, to begin with, we start with a system of stochastic differential equations for two processes. Let us denote those processes by xt and yt for simplicity. So, for example, in the case study which is under your development, xt could be USD ruble exchange rate. YT could be euro ruble, for example. Or anything like that. How can we model not the individual stochastic dynamics of xt and yt? That's not that much interesting. That was the first step we were doing. But how can we model the joint stochastic dynamics of both processes? Okay, we will model the joint stochastic dynamics via a pair of coupled stochastic differential equations. Let me, because in general there could be any setup. Well, let's start with the most general one. So in general, we would have the differential of the vector xt, yt would be equal to some vector function mu, obviously of dimensionality 2, of xt, yt, and possibly the current time t, dt, plus this is the torrent, now multidimensional torrent, plus we need to model the volatility somehow, the stochastic innovations using Brownian motion as our building blocks. There are therefore two Brownian motions which derive those stochastic processes. So xt, we suppose, is driven by the Brownian motion. Well, both of them, let's say, are driven by Brownian motions, which we denote by, let's say, wt and zt. And they are interleaved, they are mixed. Because they are mixed, then we would have, in general, some vector of the Brownian motions, increments of the Brownian motions, dwt and dzt, And we would have some matrix function, which I will denote by, how shall we denote it? We'll denote it by, let's say, sigma, which depends on, again, xt, yt, and possibly t explicitly, multiplied by this vector. So that's how, in general, it would look like at the moment, and this is obviously the volatility matrix. In this general formulation, the problem is really too general, so we cannot do much exploring this. It is far too general. But let us consider a more tractable, more specific type of problem. So first of all, we assume that our vector function mu, you already remember, if we don't know anything, we make an ansatz. You remember that. So, okay, if we don't have any specific structure for mu, what do you think the most natural and simple assumption we can make about mu? That it is constant, maybe, but we'll take it a little bit too further, and we'll assume that mu is linear in xt and yt. Therefore, the vector function mu can be written as some linear combination for the first component. Let me denote it by a1 xt, where a1 can actually depend on t, may or may not, plus a, let's say, b1, which may depend on t, yt, plus some c1 of t. And similarly for the second component, it would be a2, which may depend on t, xt, plus b2 of t, yt, plus c2 of t. Regarding sigma, it is a little bit more interesting, actually. Let us explore what it actually means. Then we'll proceed with more precise definition of our function mu, and we'll proceed with our definition of the model. For the moment, let me write my matrix sigma in the general way as, let's say, sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2, where all entries of this matrix, sigma ij, are actually functions. In general, we don't know what it is, but for the moment we assume it is, they are functions of xt, yt, and t in general. So then suppose that we are currently at some function, at some point in time t, and we have xt and yt already known at that point. We reach some function t, we know t, xt, yt. Then the Brownian motion increments dwt, dzt, if you remember, are independent of the current state of xtyt. No matter where we are, we just have new random ticks of normally distributed Brownian motion increments. And you remember that both of them have a normal distribution, n of 0 square root of dt, same for zt. And we will assume that the Brownian motion wt and zt are independent, that's important, independent from each other. You may ask whether it is a too restrictive assumption. I would say no, it is not, because precisely the effects of joint action of dwt and dzt is modeled by application of the matrix sigma, which provides a mix of our Brownian motion increments, dwt, dzt. So we can safely assume they're independent, and any combination effect of them is precisely achieved by applying the matrix sigma to the vector of independent Brownian motion increments, dwt, dzt. What does it mean exactly? So we would have, if we expand it a little bit, we would have, just to reduce writing, I would write the mu vector as mu1, mu2, and you understand that the components of mu1, mu2 depend on xt, yt, and t. Then we would have dxt equals to mu1 of all of them dt, plus, by applying the matrix sigma, we would have sigma 1, 1 dwt plus sigma 1, 2 dzt. And similarly, dyt equals to mu2 dt plus sigma 2, 1 dwt plus sigma 2, 2 dzt. Once again, mu I and sigma ij are functions of xt, yt, and t. Let us pay some attention to this part. I will scroll my screen a little bit. So, at time once again, at time t, we would have sigma 1, 1 and so on, sigma 2, 2 to be known or fixed. Why? Because they depend on xt, yt, and t, which are all known at that point. Okay. What would then be a linear combination of, let's say, sigma 11 dwt plus sigma 12 dzt? Well, each of them is a normally distributed random variable, so this one would also be normally distributed. And we can say, what are the parameters actually of this normal distribution? We'll see it in a second. Let us denote this. So first of all, obviously it is normally distributed with zero mean. And can you tell me please, what is the standard deviation of, first of all, why is it zero mean? And what is going to be a standard deviation of this random variable? Anyone please tell? Do you remember the properties of a Brownian motion? I think we have discussed them in quite a detail. Did we? Okay. Multiplication of sigmas. Okay, multiplication of sigmas. Not exactly. Let's work it out. You know, ladies and gentlemen, may I really seriously say that dealing correctly with normally distributed random variables is a very important thing which you ought to deal with correctly. Of course, not multiplication of sigmas. So what we have, first of all, why the mean is 0? Simply because the mean is the sum of means of these two random variables. So the expected value or the mean of sigma 11 dwt plus sigma 12 dzt. The expected value is a linear operation, so it is sigma 11 expected value of dwt, which is obviously 0, plus sigma 12 expected value of dzt, which is obviously 0 as well, and therefore we get 0. Now, what we can say is that let us compute the quadratic variance of this random variable. The quadratic variance, if it is the variable itself is of 0 mean, then the variance of this random variable would be just the expected value of its square. Okay. So we'll say that variance of sigma 11 dwt plus sigma 12 dzt. In this case, it is the expected value of its square in this case because the mean is 0, obviously. Okay, let's square them up. So this is the expected value of, we just take the square, sigma 1 squared dwt squared plus 2 times sigma 1 sigma 12 dwt dzt plus sigma 12 squared dzt squared. Okay. Applying this expected value as a linear combination, we have once again sigma 1 squared expected value of dwt squared plus 2 times sigma 1 sigma 12. In general, we must say the expected value of the product, which may or may not be equal to the product of the expected values. So be careful. At least don't do it without a good reason. Plus sigma 12 squared expected value of dzt squared. Now, this is equal to, let's deal with the squares first. The expected value of a square of a Brownian motion increment is the quadratic variance of the Brownian motion increment, which we know is equal to dt. So we have sigma 1 squared plus sigma 12 squared times dt plus 2 times sigma 1 sigma 12. And now I said that these Brownian motions dwt and dzt are independent. We mentioned that. Okay, they're independent. For independent random variables, the expected value of the product is equal to the product of expected values. That's very well known. And obviously, each of these expected values is 0. And therefore, this cross term, which contains both dwt and dzt, yields 0. So eventually we got sigma 1 squared plus sigma 12 squared. Therefore, in the normal distribution, we write not the quadratic variance, but by our convention, we write the standard deviation. Now, for the standard deviation of this linear combination is going to be square root of sigma 1 squared plus sigma 12 squared. Yes, and then we multiply it by dt and multiplied under the square root multiplied by dt. So that's what the standard deviation of our linear combination is. So basically up to a scaling factor, which is in this case the square root of sigma 1 squared plus sigma 12 squared, we get this linear combination of the Brownian motions to be yet another Brownian motion up to a factor. So we can say that this is equal to the square root of sigma 1 for this linear combination, not for the distribution. We say by factoring out this square root, we can write it as sigma 1 squared plus sigma 12 squared square root times some new Brownian motion, which I denote by dut, which is a Brownian motion as well, which has a normal distribution with 0 mean and the standard deviation being the square root of dt. That's what this linear combination does for us. And in a very similar way, the second line of our equation would be expressed through another Brownian motion. So what we can now say is that for fixed, of course, for fixed t, we would say that dxt, as we said, is the function mu1, which depends on xt, yt, and t times dt, plus square root of sigma 1 squared, which depends on all same arguments, plus sigma 1 squared, which depends on the same arguments, times dut, where dut is another Brownian motion. And similarly, dyt would be equal to mu2 of xt, yt, and t times dt, plus square root of sigma, now we understand, 1 squared, plus sigma 2 squared, times another Brownian motion dvt. dut and dvt are Brownian motions, but they are not independent anymore. So once again, you remember that what is dut? dut is sigma 1 dxt plus sigma 1 dyt divided by this square root, sigma 1 squared plus sigma 1 squared. In a similar way, dvt is sigma 1 dxt plus sigma 2 dyt divided by the square root of sigma 1 squared plus sigma 2 squared. While, sorry, not dxt, apologies, dwt, dzt, sorry, and here we have for the Brownian motions dwt and dzt. Sorry. So while dwt, dzt are independent, dut, on the other hand, and dvt are in general correlated. So it is relatively easy to compute the correlation and covariance between these modified Brownian motions, which are linear combinations of the original Brownian motions. So let's do that. The covariance, let's start with the covariance first. Covariance of dut, dvt in this particular case, because they're all centered, so they have zero mean. For that reason, because mean is 0, the covariance is equal to the expected value simply of the product dut times dvt. Okay, and we know what they are. So by computing the product, so just multiplying dut and dvt, first of all, we'll factor out the coefficients. Sigma 1 squared plus, sorry, here there's a typo, sigma 1 2 obviously, plus sigma 1 2 squared and the square root of sigma 2 1 squared plus sigma 2 2 squared, and then the expected value of the corresponding product of the numerators. But again, as we already know, the cross product of double dwt and dzt has zero expected value because these normally distributed random variables are independent. Therefore, we only have products of sigma 1 1, sigma 2 1. So we would have immediately sigma 1 1, sigma 2 1. Here, yes, as Daniel pointed out, here in this particular case, we do indeed encounter the products of sigmas. In this case, yes. So it is sigma 1 1, sigma 2 1 dwt squared plus sigma 1 2, sigma 2 2 dzt squared. But dwt squared is obviously equal to dt, dzt squared is equal to dt as well, and therefore we get sigma 1 1, sigma 2 1 plus sigma 1 2, sigma 2 2 divided by the same square roots as above times dt. So that's the covariance. Now, the correlation is very easy to determine. Let me move my screen up. Once we know the covariance, the correlation is very easy to find. So the correlation between these new Brownian motions d ut dvt would be equal to the covariance between them divided by the standard deviation, product of the standard deviations of both. Standard deviation dut times standard deviation of dvt. But we have already demonstrated that these dut and dvt are Brownian motions. Therefore, the standard deviation of both of them are equal to the square root of dt. Therefore, the product is simply equal to dt, which cancels the dt factor in the numerator. And therefore, we finally have the covariance being equal to sigma 1 1, sigma 2 1 plus sigma 1 2, sigma 2 2 divided by the square root of sigma 1 1 squared plus sigma 1 2 squared, square root of sigma 2 1 squared plus sigma 2 2 squared. So that's the correlation. Starting with, so you see what we got. We started with independent Brownian motions, dwt, dzt. They were independent. We applied the matrix sigma to this vector, dwt, dzt. And by application of this matrix sigma, we got, you remember what it was? We got, let me scroll it down. By applying the matrix sigma, we got these factors, square roots, applied to this new vector of the Brownian motions. So sigma applied to this would be equal to a vector square root of sigma 1 1 squared plus sigma 1 2 squared times the Brownian motion dut and square root of sigma 2 1 squared plus sigma 2 2 squared applied to the Brownian motion dwt. So these are independent BMs, dut, dvt are now correlated Brownian motions, Brownian motion increments actually, where the correlation coefficient is given by this expression. That's the correlation coefficient between them. Starting with independent Brownian motions, we got correlated Brownian motions. So taking a linear combination of two Brownian motions which are mixed together this way, and both of them derive our stochastic process dxt and dwt, we get really correlation of random increments in the stochastic dynamics of this process. That's how we in general get correlations. It is always possible to assume that we start with independent Brownian motions, but through application of a certain matrix to the vector of those Brownian motions, we get the resulting stochastic factors deriving our random variables, dxt and dwt, we get them correlated. But this correlation is not the only way of how they depend on each other. As you remember, there is also a trend term, mu. And in this trend term, mu, we have linear dependencies of mu1 and mu2 on both x and y, which also give rise to dependencies between them. This is not correlation. This is something different, which is actually called co-integration. And we should distinguish between these two cases. Let us make a short break, maybe 5 minutes, and we'll continue investigating our joint stochastic dynamics of xt and yt, and then we'll see what we can make of it. So 5-minute break, and then we resume. Okay, let's go further. One more thing I would like to do probably before exploring the trend terms which are proportional to dt is to simplify our notation a little bit. So let me do the following. I will use the notation just to reduce writing. I will use the notation a1 being precisely this square root of sigma 1 1 squared plus sigma 1 2 squared. A2, as you can easily guess it, this one is square root of sigma 2 1 squared plus sigma 2 2 squared. Remember that in general all sigmas may depend on and do depend in general on xt, yt, and zt and t itself. They are not constant in general. So in this case we can write dxt equals to mu1 of xyt dt, where mu1, if you remember, is a1 xt plus b1 yt plus c1, plus I can say it is in this case a1 d ut dyt equals to mu2 dt, which is a2 xt plus b2 yt plus c2 under our assumption, plus a2 dvt. And these two stochastic processes, a1 dut and a2 dvt, they are correlated because dut dvt are correlated. So let us denote by C capital. I would like to do the covariance matrix of this process. So once again, it will be very close to what we have obtained, but let's do it formally. It will be helpful for us. So what we do, we say once again, we say, let's see, being the covariance matrix of these two processes. Covariance matrix of these two processes. Let me denote it just covariance matrix of a1 dut and a2 dvt. So what are the covariance? What would be the covariance matrix? The covariance matrix would be the covariance. It is a 2 by 2 matrix. The covariance of the first process by itself. The covariance of the first process by itself is obviously the variance of this process. So I do not even put covariance here. I immediately put the variance. So it is the variance of a1 dut. Here it is covariance of a1 dut plus A2 dVt. Here it is the same thing. So obviously the covariance matrix is a symmetrical one. It is same covariance here of A1, sorry, not plus, just covariance, comma, covariance A1 d ut A2 dVt, and the variance of the process A2 dVt. Okay, let us consider this matrix further. So let's begin with the first variance. So what is the first variance? The first variance is obviously as the expected value of a square. The variance is A1 squared times variance of dut. Okay. The covariance is of these two processes is the product A1 A2 covariance of dut dvt. Here we have again the product of A1 A2 covariance of dut dvt, and here we have A1 squared variance of dvt. Continuing. So obviously what the variance of dut and dvt is, we know. That's pretty simple. It is dt. It is a Brownian motion, and the variance of a Brownian motion is equal to dt. Now, for covariance of dut and dvt, let us scroll up and see, because we have already got the formulas for this process. What have we got? We got the correlation between them, and the covariance between them is simply equal to the correlation times variance. So once again, please take a note. So the correlation between dVt and dWt, I will write it here. So by continuing with this formula, we can say what is the correlation. The correlation is precisely sigma 1,1 sigma 2,1 plus sigma 1,2 sigma 2,2 divided by the product of A1 times A2. Okay, and covariance between them is the same as correlation between them multiplied by the standard deviation. So excuse me, I will write in this corner. So covariance between dut dvt equals to the correlation between dut dvt times square root of dt, which is the standard deviation of the first one, times square root of dt, which is the correlation of the second one. And therefore, it is correlation times dt, and the correlation is equal to sigma 1, 1, sigma 2, 1, plus sigma 1, 2, sigma 2, 2, divided by a1, a2, and therefore we multiply everything by dt. Okay. Which allows us to rewrite this entry of our matrix you see we have a product of a1, a1, a2 here times covariance, and the covariance formula contains division by a1, a2, so here we have the covariance, which is equal to, as we have just seen, sigma, what is the covariance? Can you remind me, please? Sigma, let's see, once again, in order to be correct, the covariance was sigma 1, 1, sigma 2, 1, 1, 2, 2, 2. Okay, therefore, it is sigma 1, 1, sigma 2, 1, plus sigma 1, 2, sigma 2, 2, divided by a1, a2, and times dt. And obviously a1, a2 would cancel. Therefore, altogether we have a1 squared sigma 1, 1, sigma 2, 1, plus sigma 1, 2, sigma 2, 2. Here the same entry, sigma 1, 1, sigma 2, 1, plus sigma 1, 2, sigma 2, 2, a, and here is a2 squared. A2 squared. And here we have a2 squared. Now recalling what sigma 1, 1 and sigma a1 and a2 are, you remember that a1 is actually the square root of sigma 1, 1 squared plus sigma 1, 2 squared, and a2 is the square root of sigma 2, 1 squared plus sigma 2, 2 squared. All right, let's check that. Where the definitions of our a coefficients are. Yes, indeed. 1, 1 squared plus 1, 2 squared, 2, 1 plus 2, 2. We finally get the following formula. So we got sigma 1, 1 squared plus sigma 1, 2 squared, sigma 2, 1 squared plus sigma 2, 2 squared. Here we have sigma 1, 1, sigma 2, 1 plus sigma 1, 2, sigma 2, 2. And here same expression, sigma 1, 1, sigma 2, 1 plus sigma 1, 2, sigma 2, 2. You remember what we are doing? We are constructing the covariance matrix of our stochastic innovations a1 d ut and a2 dvt. But we can even take it further, because you can see in a second, you remember that sigma entries are the entries of the original sigma capital matrix. So this is nothing else but the matrix product sigma times sigma transposed. You'll see it in a second why. Yes, indeed, because sigma is, you remember, sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2, and therefore sigma transposed is sigma 1, 1, sigma 2, 1, sigma 1, 2, sigma 2, 2. And now we see indeed by multiplying rows by columns, sigma 1, 1 squared plus sigma 1, 2, sigma, just a second, or the way around, sigma, what do I put here, sigma, to the typo, sigma 1, 1 squared plus sigma 1, 2 squared, not 1, 1. Okay, so sigma 1, 1 squared plus sigma 1, 2 squared, all right. This one, sigma 1, 2, sigma 2, 1, sigma 1, 1, yes, plus sigma 2, 2, sigma 1, 2, yes. This one is obviously the same, and the final one is sigma 2, 1 squared plus sigma 2, 2 squared, yes. So that's what we wanted. So the correlation matrix C, our result is C, which is the covariance matrix of A1 dUT, A2 dVT, sorry, dVT, appears to be equal to sigma times sigma transposed. That's what we wanted. Now, let us examine the linear term. So this allows me to write our joint stochastic dynamics of, you remember our initial observable process xt and yt. You may have forgotten actually where we started with and why we're doing this. So I will recall. We have xt, which is, for example, USD. We have yt, which is, for example, EURB. We got stochastic dynamics for them, dxt equals to A1xt plus B1yt plus C1 all times dt plus A1 dut, which is a stochastic innovation because dut is a Brownian motion. Dyt equals to A2 xt plus B2 yt plus C2 times dt plus A2 dVt, as we have shown, and the covariance matrix between these two is what we defined by C and what appeared to be the product of sigma times sigma t in our original setup. Okay, so we know what happens with the covariance here. In particular, this covariance, up to normalization, it is a correlation between the stochastic increment of the first process and the second one, sigma 1, 1, sigma 2, 1 plus sigma 1, 2, sigma 2, 2. It can be both positive and negative. So the correlation between this process may be either positive or negative, and the correlation, as we know, it stands for the statistical dependency on those stochastic increments of the Brownian motion ticks. But there is also a dependency here in the trend, because obviously both terms for xt and yt, they do depend on both xt and yt. Let me examine it in a very simple case. I suppose that AI, BI, CI are for the moment constant. This is just simple. We don't need to consider them constant. They could be functions of time, but let's say for the moment we assume that they are constant, or they are constant at a given time t. And let me completely forget for the moment about the stochastic part. So instead of our stochastic differential equation, I will consider truncate the stochastic part. We get a two-dimensional ODE, ordinary differential equation. So basically, in this case, in a vector notation, d xt yt would be some matrix A1, B1, A2, B2, multiplied by our vector xt yt, plus vector c1, c2, all multiplied by dt, and there is no stochastic term in this case. So let me denote this matrix by A, this vector by C, and our xt yt vector by a vector x. X is not good because you can very easily get confused. Let me denote it by vector xi. So then I have in the vector matrix notation dxit equals to A times xit plus c dt. Or, because there is no stochastic term here, I can really replace differentials with derivatives, which is not possible when we have non-differentiable Brownian motions on the right-hand side. We have xi dot t. Dot means differentiation with respect to time. Dot means differentiation with respect to time, right? Xi dot t equals to A times xit plus c. A very simple, in this case, two-dimensional system of ordinary differential equations. What do we do with such a system? For the moment, we can't solve it, but we can separate the variables by transforming our matrix into a diagonal form. You remember how to do it. So basically, we will apply a linear transform in order to put the system into a more simple form, actually. So apply a linear transform. Apply a linear transform. Some transform M, some matrix M, such that we will introduce a new vector of variables, eta, so that the original vector xi or other way around, it doesn't really matter. Let's say the new vector would be equal to m xi. It also depends on t. Or originally we would say psi t is the inverse of our matrix M multiplied by the vector eta. By substituting this expression into our ordinary differential equation, we'll get psi dot t equals to, on the one hand, it is inverse of m mu dot t, but on the other hand, from the equation, it is a times psi t plus c, which is, and we know that psi t is the inverse of eta t, m inverse eta t, therefore it is a times m inverse eta t plus c. And by combining these two equations, multiplying, they're equal, obviously, multiplying this on the left by m inverse, we finally get eta dot t in the new coordinates eta equals to m a m inverse eta t plus mc, where mc is another vector, it can be denoted by gamma, doesn't matter. So what is this? M inverse is basically the matrix A expressed in new coordinates, precisely in the coordinates eta. We can, in the generic case, we can construct the transformation M in such a way that M inverse would have a diagonal form. And this diagonal form is equal to lambda matrix, which is lambda 1, 0, 0, lambda 2. How can we do it? In this case, basically M inverse must be a matrix of, now let's stop here and recall our first year linear algebra. How can we transform matrix A into the diagonal form? We apply the transformation. Normally the transformation is written other way around, M inverse AM, and that's why I say M inverse must be a matrix of what? Type in, please. I open the chat for that. How do we put our matrix into the diagonal form? What do we do to that end? And what are lambda 1 and lambda 2 here? First year linear algebra. Ladies and gentlemen, please. What are lambda 1 and lambda 2? Okay. Lambda 1 and lambda 2 are called eigenvalues, you remember, of A. M inverse in this case is a matrix of eigenvectors. Of A. And in the generic situation, not always, but in the generic situation, we would have actually eigenvalues can be both positive and negative. Moreover, let's see that they might not, in the very general situation, they might not even be real, because for the eigenvalues we would have a quadratic equation which defines them. But if they are real, assume in this particular situation that lambda 1, lambda 2 are real. In this case, in terms of the new coordinates eta, we now have a very simple equation. I mean, dropping the stochastic part, we would have eta 1 dot would be equal to lambda 1 eta 1 plus gamma 1, and eta 2 dot would be equal to lambda 2 eta 2 plus gamma 2. Now a very, very, very important thing is about the sign of our lambdas. Suppose that, again, assume once again that at least one of the lambdas, or maybe both, but we need at least one, let's say lambda 1, is negative. What does it mean? Consider this ordinary differential equation with negative lambda. Even for the moment, okay, how can we solve this equation actually? What would be the solution? No matter whether it is negative or positive, if we have an equation of this form, the solution would be, it is an inhomogeneous linear differential equation. So initially drop the constant term, we would have eta 1 dot simply equals to lambda 1 eta, and therefore we get eta 1 of t, the function of t, equals to some constant, don't confuse it with our covariance matrix, but I will call it C1 for the moment, exponent of lambda 1 t, that's the general solution, plus some solution to the inhomogeneous equation. If you remember from the ordinary differential equations, but what is the inhomogeneous one? If gamma is a constant, then we would be searching for a solution as a constant as well. So substituting a constant, we would have 0 here, lambda 1 times constant plus gamma 1 equals to 0. And therefore, this constant would simply be equal to minus gamma 1 divided by lambda 1 in this case. All right? All right. Assuming that it is not 0. And if gamma 1 is negative, this means that mu1 of t would tend to a limit as t tends to plus infinity, which is equal to minus gamma 1 divided by lambda 1. What does it mean? You remember that eta is just a linear combination of our certain A1, A2 vectors. So basically, because we just changed our linear basis, our lambda, our eta 1 of t is some, let's say, alpha 1 x1 of t plus some would say beta 1 y1 of t, and that linear combination would tend to a limit which we know now is minus gamma 1 divided by lambda 1. What does it mean? This effect in financial terms is called mean reversion, not of the individual price x1 or y1, x or y. There is no x or y. Not just of individual prices x or y, but a linear combination of them. So we have a linear combination of x and y such that this linear combination decays in time. It doesn't blow up, it doesn't go to infinity with the exponent, it decays in time, and it converges to a certain limit. And obviously, the more negative lambda 1 is, the faster this convergence is. This is precisely the effect of mean reversion of our tradable assets. This is the mean reversion of a linear combination of x of t, y of t. What does it mean? It means that in financial trading terms, if you constructed a portfolio of, let's say, alpha 1 units of x, which is in our case USD ruble, and beta 1 units of y, which is euro ruble, typically the values of alpha 1 and beta 1 will be of opposite sign in this particular situation, but it doesn't really matter that much in our case. So if they are of different sign, then we take long position in one financial instrument and short position in the other. If they are of the same sign, just by chance, for example, then we would take both long or both short position, but that's extremely unlikely. That's extremely unlikely. So if we construct this portfolio, then the value of this portfolio converges to a constant. Which constant? This constant. Which means that when the value is above the constant, we can assume that due to this mean reversion, and mean reversion is due to co-integration, which is due to the linear structure, the structure of our term, linear terms in the stochastic dynamics of x and y. If this linear combination is above this value, then there is a tendency for it to go back to this value, decay, decrease. If it is below this value, because asymptotically it would tend to this value, then there is a trend for this portfolio value as a linear combination to increase. This is precisely how a pair trading strategies are in general implemented. So what we have discovered is a quantitative foundation of pair trading algorithmic strategies. In particular, such algorithmic strategies can be implemented using this USD ruble and euro ruble instruments in general. If we prove that indeed, after we calibrate this model, compute all our coefficients A, B, C, A1, B1, C1, and so on, that the corresponding matrix A does indeed have at least one negative, or we prefer strongly negative eigenvalue. That's how it works. But why did we construct also the covariance matrix beforehand? Because if we just not only want to establish under the deterministic assumption, the last result, you remember, was obtained when we cut the stochastic part off, but we would like to explore in more detail the probabilistic properties of our trading strategies, how fast it would converge to the mean, what is the probability of it not converging. So we would like to make more quantitative signals out of it. Then we need to take into account both the trend term, which we examined in the second part of our lecture, and the covariance term. How to do it in more detail and how to calibrate this type of model, I can talk now about this and for ages, but I believe that the time is high to stop now, and we'll consider this topic, continue this next week. Thank you, and I'm prepared to answer your questions, please. No questions. Everything is perfectly clear. Next time we're launching an algo trading strategy altogether. Wonderful. Thank you very much. See you next week. Thanks.